First one is number 2. We give you 3 points, P, Q, and R. And we want to show one of the angle is very special, right? It's a 45-degree angle. If you draw the picture, draw the diagram, you almost see Q is what? It's the one that is special, it's 45 degrees. But we also want the students to make sure they don't do trigonometry, because if this kind of thing you do trigonometry, then what's the point, right? So how do I basically doing reverse engineer about solving a problem, right? We know we want to show that's 45 degrees. So the easiest thing for me to show is there's involving a what? Isosceles right triangle. That's how I do it, right? So I look at this direction PQ is basically 3 and a 21. The movement, right? Yeah. Right? So it's basically 3 times of what? 17, right? So it goes right to yeah, right 3 and 17. So if I want to produce isosceles right triangle, that means I need to find something perpendicular to it. Right? To make that 45, 90 out. Right?
Perpendicular to PQ or perpendicular to PR?
I would say I want, okay, so that's a good question. Right, where do I draw this perpendicular, right? I know 45 degree comes from right triangle is 1:1 ratio, right? So I have to take a look at my side lengths. 1/7 movement is basically root 50, right? 1 squared plus 7 squared, you move the root 50, right? And I look at the RQ, how long is that? That's 8 squared plus what? 6 squared. 8, 6. 6, 8, 10. So their length, RQ is basically what? RQ is basically 10, right? So this is 10. And this one has 3 times of what? 1/7. And the 1/7 is root what? 50. So 10 and the root 50 are very nice. If it's isosceles triangle, it's exactly follow what? 1 and the root 2 ratio, right? So that means what? If I do 10 here, and this were really 45, if I go down what? Root 50, then I should have a what? Right triangle, right?
So you're saying that we'll cut PQ into 3 segments.
3 segments, right? You want to do that?
Yeah, sure. So you said this one was 10, and then if we cut this into 3 equal segments, this part will be root 15. All of them will be root 15.
Right. So if I connect these two, they should give me what? Root 52, right? If I do reverse engineer. So now I know very clearly now what do I do now? Because I can easily find this point, right?
So this point will just be, we'll have 1/17 and 1 more. So this will be going 2 right and 14 up. So this will be 7 and 14.
Right. And then I can clearly check this is what? 7, 1 also, because the distance is this. So I know how to cut my grid, right? Right? So that covers this part.
Can I say something about it? So this thing did a student in my class. So she projected from R to PQ, right?
R to PQ, yes.
But the thing is that R and Q are 2 lattice points. And when we look at, if you take any 2 lattice points and you draw this perpendicular, you not always know if it's going to be that projection to be lattice. That 714 is just because of these numbers. You said it's good.
Yes.
But I think what I know, if R and Q are lattice points, and I draw the projection this way, then
you're guaranteed to be
a lattice
okay,
point.
let's do
Minji,
that.
can you do that?
So you're saying
I draw perpendicular to RQ and R.
Yes. So that's a very nice way of doing this also.
It's right.
Yes. But technically it has to be this second point,
It should
right?
be the second.
So that's a very nice thing. Over here we are not sure if this is what? A lattice point. But if we turn this movement to 90 degrees, we are sure this has to be lattice point, right?
Right. Because we're just taking this right triangle
Uh-huh.
and then we're turning it sideways.
Yes.
So it has to be
A lattice point. Yeah. So that's another way of seeing this. Use tab. right?
And at the end, we need to prove that it's isosceles, so we use distance formula, right?
Right.
In both of
Yes.
these solutions.
So this just gives us a better idea about numbers in two dimensions, right? Okay, have a good sense of it. And then, well, this problem actually is very helpful for our next problem. I hope our audience understand why we suddenly throw a very simple problem here, because this actually is big time helpful for the next problem. Okay? So now I want to talk about this problem. I'm going to talk about it in two stages. One is I want to show people a log proof. You cut the board this way, as we indicated, 4 pieces, right? So somehow there's a zigzag here. So you put this corner into here. So now you have a wonderful 4x4, right? But on the other hand, this tube, the only thing you can put in, because we can only allow translation. So this one slides in here, you are in trouble. This is not even a playing field of what 3x3 chessboard anymore, right? So as a cut as a dissection for rectangles, this is fine. But as a dissection for chessboard, now we're in trouble. Okay? So this problem in a certain way is a little bit challenging, right? And this is an extension of that 9x16 staircase, right? But this is more interesting. How do we build a staircase basically involving the fields are preserved? So now we're going to talk about 2 of those cuts that are possible. And both of them involving just cut out a 2x2 piece first. Okay, so we give our audience a help. You can try either way, but in each way of them, this is one of the pieces, the 2x2.
But in general, we try to minimize the number of pieces.
Right.
So 3 is probably impossible.
Right. I do not know how to prove 3 is impossible. All the things I know is 4 is possible.
Yeah, so there are 4 pieces that you assemble to get